Picture a vast open savanna, roughly 2 million years ago. The landscape is almost entirely grass. Endless, swaying, golden green grass stretching to every horizon, interrupted occasionally by a thorn tree or a dried riverbed. It covers the ground in every direction, more biomass per square mile than almost anything else in the environment. It's free, it's abundant, it never runs away, it doesn't fight back, it doesn't require a spear, a trap, or any particular intelligence to locate. And your ancestor, a small, lean, sharp-eyed hominin standing in the middle of all of it, is absolutely starving. Not because there's nothing to eat, because the single most abundant food source on the entire continent is, for all practical purposes, completely useless to them. They could pick up a handful of grass right now, chew it until their jaw aches, swallow it, and extract almost nothing nutritionally meaningful from the effort. Meanwhile, a wildebeest standing 20 feet away is doing exactly that, eating grass, thriving on grass, building hundreds of pounds of muscle from grass, and your ancestor is watching with whatever passed for existential frustration at the time. This is one of the most underrated paradoxes in the entire story of human evolution. Grass is the most successful plant family on Earth. It covers roughly 40% of the planet's land surface. It feeds the largest animals alive, and humans, intelligent, adaptable, tool-using, endlessly resourceful humans have never meaningfully eaten it. Not 2 million years ago, not today, not in any famine or desperation that history has recorded. Why? What is it about grass that puts it so thoroughly outside the human dietary range? And what does the answer reveal about the strange, particular, surprisingly fragile machine that is the human digestive system? To understand the grass problem, you first need to understand what grass actually is at a chemical level, because the answer isn't obvious from the outside. Grass looks simple. It's a plant. Plants are food. Humans eat plants constantly. Fruits, roots, tubers, leaves, seeds, bark, in some cases. The idea that an entire category of plant could be essentially off the menu seems almost arbitrary until you look at what grass is built from. The primary structural component of grass is cellulose. Cellulose is a polysaccharide, a long chain of glucose molecules bonded together. And here's the thing. Glucose is one of the primary fuels the human body runs on. Your brain, your muscles, your organs, they all love glucose. Cellulose is, in a sense, a storage unit absolutely packed with glucose molecules. There is enormous caloric potential locked inside every blade of grass. The problem is the lock. Cellulose chains are held together by a particular type of chemical bond, a beta-1 for glycosidic bond, that the human digestive system cannot break. Humans do not produce cellulase, the enzyme required to cleave those bonds and liberate the glucose inside. Without cellulase, cellulose passes through the human gut entirely intact. You can swallow a handful of grass, and it will travel the entire length of your digestive tract, encountering stomach acid, bile, pancreatic enzymes, and the full suite of intestinal machinery, and emerge on the other side chemically almost unchanged. Your body will extract a handful of water and minor minerals and nothing else. The cellulose wall is impenetrable. This isn't a minor limitation. It means that the primary structural material of the most abundant plant group on Earth is, for humans, completely indigestible. The grass is full of calories the way a locked safe is full of cash. You know it's in there. You cannot get to it without the key. And evolution never handed humans that particular key. So why do cows get the key and humans don't? This is not a rhetorical question. Ruminants, cows, sheep, goats, deer, buffalo, and dozens of other species eat grass constantly and thrive on it. They are, in metabolic terms, extraordinarily good at extracting nutrition from cellulose. Understanding how they do it makes the human limitation much clearer. Ruminants don't produce cellulase themselves either, strictly speaking. What they have instead is a gut architecture specifically designed to host the microorganisms that do. The rumen, the first and largest chamber of a ruminant's four-part stomach system, is essentially a massive fermentation vat. It holds tens of gallons of microbial soup, bacteria, protozoa, and fungi that have been specifically selected by millions of years of coevolution to specialize in breaking down cellulose. When a cow swallows grass, it lands in the rumen and sits for hours. The microbial community goes to work, fermenting the cellulose, breaking the bonds, producing volatile fatty acids that the cow then absorbs absorbs and uses for energy. The cow periodically regurgitates the partially digested material. This is what chewing cud actually means, and rechews it to break it down further before swallowing again. The entire process is slow, elaborate, and requires a digestive system that devotes enormous physical real estate to fermentation infrastructure. A cow's gut is, by body weight proportion, massive. The whole ruminant system, rumen, reticulum, omasum, abomasum, represents a significant fraction of the animal's total body mass. The entire architecture of the ruminant body is organized around the challenge of extracting nutrition from cellulose. Now look at the human gut. By comparison, it's compact, efficient, designed for rapid processing of calorie-dense, easily digestible material rather than slow fermentation of fibrous plant matter. The human stomach is a single chamber. Total gut transit time in humans runs roughly 1 to 2 days. Ruminant digestion can take 3 to 4 days for the same volume of material. Humans simply don't have the fermentation capacity, the chamber architecture, or the specialized microbial community to run the grass digestion process even at a fraction of ruminant efficiency. But hold on, because this is where the story gets more interesting than a simple wrong gut explanation. Humans do have gut bacteria. The human microbiome includes microbial strains capable of modest cellulose fermentation. The large intestine, where most of this microbial activity occurs in humans, does extract some short-chain fatty acids from fermented plant fiber. This is in fact exactly what dietary fiber does in the human body. Soluble fiber in particular reaches the large intestine relatively intact and gets fermented by gut bacteria, producing butyrate, other compounds that feed colon cells and contribute to metabolic health. So the machinery for fermenting plant fiber isn't entirely absent. It's just dramatically undersized for the job grass requires. The human large intestine can handle modest quantities of soluble, easily fermented fiber. It cannot handle the industrial-scale cellulose load that a diet of grass would require. Trying to live on grass wouldn't just be nutritionally futile, it would be actively problematic. The fermentation of large quantities of indigestible material produces gas. A lot of gas. Bloating, cramping, and significant digestive distress would accompany any serious attempt to eat grass as a dietary staple. Your gut would protest loudly and continuously before ultimately failing to extract enough calories to sustain life. There have been documented cases of severe human starvation in which desperate individuals attempted to consume grass. The outcome was consistent. The grass provided essentially no caloric relief, digestive symptoms were severe, and the individuals remained starving. The human body simply cannot run on it. Now, here's a distinction that matters enormously, and that most casual treatments of this topic completely miss. Humans can eat grass seeds. This is not a minor asterisk. This is the entire story of civilization. When we say grass, we're talking about the family Poaceae, a group that includes wheat, rice, corn, barley, oats, rye, sorghum, millet, and dozens of other species. Every single one of these is a grass. The seeds of these plants, the grains, have a completely different nutritional profile than the leaves and stems. Grain seeds are packed with starch, a polysaccharide composed of glucose chains held together by alpha bonds, which human digestive enzymes break with ease. Seeds also contain protein, fat, and a range of micronutrients. Seeds are calorie-dense, digestible, and storable. The grass itself, the stems, the leaves, the blades, is cellulose and silica, and almost nothing the human gut can use. But the seed is a completely different biochemical package. This distinction is the foundation of the agricultural revolution. When humans figured out how to cultivate grass species and harvest their seeds at scale, everything changed. But it's worth noticing that this is a workaround, not a solution. Humans didn't figure out how to eat grass. They figured out how to exploit the most digestible fraction of specific grass plants while discarding everything else. The cow eats the whole plant. The farmer harvests only the seeds. The silica angle deserves its own moment because it's one of the stranger defenses in the plant kingdom. Grass contains significant quantities of silica, essentially the same material as glass, deposited in and around the plant cells. This silica serves as a structural reinforcer and, critically, as a defensive mechanism against herbivores. The microscopic silica crystals embedded in grass leaves are abrasive enough to cause measurable wear on the teeth of animals that eat it regularly. Grazing animals have evolved specific dental adaptations in response to this. Horses and other grazers have hypsodontic teeth, high-crowned molars with thick enamel that can withstand continuous abrasion. As the surface wears down, fresh enamel is exposed. These teeth are effectively self-renewing in functional terms, sacrificing height over a lifetime to maintain a usable grinding surface. Horse teeth are so tall relative to jaw depth that most of the tooth is hidden below the gum line, gradually erupting over the animal's lifespan as the exposed portion wears away. Human teeth are nothing like this. They're brachydont, low-crowned with a thin enamel layer optimized optimized for processing a variety of foods rather than sustained, abrasive grinding. A diet of grass leaves would wear human tooth enamel down rapidly and destructively. Teeth don't regenerate in humans. Once the enamel is gone, it's gone. Archaeological evidence of populations with diets heavy in gritty, abrasive plant material consistently shows accelerated dental wear. A grass-heavy diet would denude human teeth within years, creating pain, infection, and the inability to chew anything effectively long before starvation did the job. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. The silica problem isn't fatal in isolation, but it adds another layer to the picture. Grass isn't just chemically inaccessible to human digestion, it's also mechanically destructive to the equipment needed to begin digestion in the first place. Here's something that reframes the whole question in an evolutionarily meaningful way. Why did any primate lineage end up with the digestive limitations humans have? The answer lies in what the primate lineage was actually optimized for, and the answer to that is ripe fruit and leaves, with a secondary emphasis on animal protein. Early primates, emerging roughly 65 million years ago in the wake of the mass extinction event that cleared the dinosaurs, were predominantly tree dwellers in tropical forest environments. The dietary staples available to them were fruit, calorie-dense, sugar-rich, easily digestible, insects, and softer plant material. This environment rewarded a digestive system capable of processing high-quality, rapidly digestible food rather than one capable of fermenting tough fibrous material slowly. The digestive systems of early primates evolved accordingly. They developed excellent sensory systems for detecting ripe fruit. Trichromatic color vision, for instance, appears to have evolved specifically to help primates distinguish ripe from unripe fruit against green foliage. They developed gut chemistry optimized for rapidly extracting sugars and other nutrients from high-quality food. They were, in metabolic terms, tuned for efficiency at the high end of the food quality spectrum. This is the opposite of what grass eating requires. Ruminants evolved from animals that processed lower quality, more abundant vegetation by throwing time and fermentation capacity at the problem. Primates evolved to find and exploit the highest quality, most digestible food sources available and process them quickly. When hominin ancestors moved out of forests into more open environments, the savanna transition that is central to so much of human evolutionary history, they were doing so with a digestive system built for tropical fruit and leaves. They had to adapt their diet to a new environment without the luxury of rebuilding their gut from scratch. What they did, brilliantly, was expand the dietary range through culture and technology, digging for tubers, processing tough plant material before eating it, hunting and scavenging animal protein, exploiting underground storage organs that other animals couldn't access. They worked around the gut limitation rather than evolving through it. Underground storage organs, tubers, corms, bulbs, rhizomes, deserve particular attention here because they may be the nutritional key that unlocked the savanna for early humans. Grass-dominated environments are not just grass. Below the surface, the same plant communities that look nutritionally useless from above are supporting extensive root systems and underground energy stores. Tubers in particular are calorie-dense, often rich in starch, and available year-round in environments where above-ground plant parts are seasonal. Early hominins who developed the ability to locate, excavate, and process these underground organs would have had access to a caloric resource almost entirely unavailable to other savanna animals. The cooking hypothesis, associated prominently with primatologist Richard Wrangham, argues that controlled fire and cooking fundamentally altered the nutritional landscape available to hominins. Raw tubers are often tough, fibrous, and only partially digestible. Cooked tubers are soft, high in bioavailable starch, and easily processed even by a relatively modest gut. The ability to cook may have allowed early Homo to extract far more nutrition from plant material than their gut chemistry alone would have permitted, effectively expanding the dietary envelope without changing the underlying digestive architecture. This is, in a sense, the human solution to the grass problem writ large. Don't evolve a rumen, build a fire. Don't become a cow, become a cook. External processing, mechanical, thermal, chemical, does the work that ruminant gut architecture does internally. The output is similar. The mechanism is completely different, and the mechanism humans chose left their hands free, kept their bodies small and efficient, and created the cultural infrastructure that eventually led to agriculture and everything downstream of it. There's an anthropological subplot worth addressing here. What happened when human populations encountered extreme scarcity? Were there not contexts in which grass consumption was attempted out of sheer desperation? The historical record is clear and it's instructive. During famines, documented across multiple civilizations and multiple centuries, people consumed extraordinary things: bark, leather, rats, insects, clay in some cases either for caloric experimentation or mineral supplementation. Historical accounts describe grinding grass seeds into paste and eating the resulting material, which is, again, using the seed rather than the plant. Accounts of people eating grass, leaves themselves typically end badly: no caloric relief, digestive suffering, and death from starvation, despite a stomach full of plant matter. The Irish famine provides one of the most heartbreaking documented examples. Reports from the 1840s describe starving individuals with green-stained mouths from eating grass in fields, a detail that became an iconic image of the catastrophe's severity. Those individuals were not nourished by what they ate. The staining was evidence of desperation, not sustenance. People were dying while surrounded by one of the most abundant plant families on Earth, unable to extract nutrition from it. There is something almost cosmically cruel about that image, and it illustrates the limitation more vividly than any biochemistry textbook. The gap between the human gut and grass nutrition is not bridgeable by hunger or willpower. Biology doesn't negotiate. The relationship between humans and grass ultimately took a different turn entirely, one that completely inverted the original dynamic. Instead of eating grass, humans figured out how to eat the animals that eat grass. This is one of the oldest and most successful dietary strategies in human evolutionary history. By hunting ruminants and other grazers, early hominins were effectively outsourcing their cellulose digestion. The ruminant does the work of breaking down grass into muscle protein and fat. The human then harvests the end product, meat, bypassing the entire cellulose problem by exploiting the animals that solved it biologically. This is a remarkable piece of ecological arbitrage. Grass is indigestible to humans. Grass is digestible to ruminants. Ruminants are digestible to humans. Therefore, the caloric content of grass is available to humans through a two-step pathway: grass to ruminant, ruminant to human. The human gut couldn't evolve to process cellulose on the relevant timescale, so human behavior evolved to exploit the organisms that could. The implications of this strategy ripple forward through all of human history. It's why pastoralism, the herding of grass-eating domesticated animals, became one of the primary economic strategies across Eurasia and Africa. It's why cattle, sheep, goats, and horses became so central to human civilization. These animals are, among other things, biological converters transforming indigestible grass into human-accessible nutrition. Every pastoral society in history was, at a metabolic level, running a distributed cellulose digestion operation using livestock as the processing units. The relationship between humans and grass runs even deeper when you consider what grass eventually became. Domesticated grass seeds, wheat in the Fertile Crescent, rice in the Yangtze Valley, maize in Mesoamerica, millet and sorghum in sub-Saharan Africa, became the caloric foundation of virtually every major civilization in history. Roughly half of all human caloric intake globally today comes from three grass species: wheat, rice, and maize. The population of the planet, currently exceeding 8 billion people, is sustained primarily by the seeds of plants that humans cannot otherwise eat. The agricultural revolution was, among other things, the ultimate resolution of the grass paradox. Unable to eat the plant itself, humans domesticated the plants, selected for larger and more numerous seeds over thousands of years of cultivation, developed processing and cooking techniques to maximize digestibility, and built entire civilizations on the caloric output. The grass didn't change. The strategy did. What's remarkable is how complete the reversal became. 2 million years ago, a hominin stood starving in a grassland, unable to eat the most abundant thing around. Today, a species descended from that hominin farms grass over more land area than any other crop type on Earth, and the seeds of grass plants constitute the largest single source of human calories worldwide. The plant that couldn't feed us now feeds almost everyone. There's a final layer to this story that touches something genuinely philosophically interesting about the nature of evolutionary constraint. Humans are often described as the most adaptable species on Earth, and in many ways, that's accurate. The range of environments humans occupy, Arctic tundra, tropical rainforest, high-altitude plateau, coastal desert, is broader than almost any other large mammal. The dietary range of humans across cultures is extraordinary. Insects, raw meat, fermented fish, blood, clay, dozens of plant families, marine mammals, fungi. Human culture has expanded the dietary envelope envelope far beyond what biology alone would predict. And yet, grass, right there, everywhere, free, abundant, calorie-rich in principle, and completely off the table, not because of culture or preference or taboo, but because of the deep, inflexible biochemistry of the human gut. One enzyme, absent. One bond, unbreakable. One family of plants, untouchable in its primary form. This is worth sitting with, because it's a window into how evolution actually works. Not as an optimizing process that produces perfect solutions, but as a tinkerer constrained by its starting materials. The human gut was built on a primate chassis optimized for high-quality tropical food. Moving into grassland environments didn't come with a blueprint revision. It came with the existing gut and the challenge of making it work in a new context. The solutions humans found, tubers, fire, cooking, hunting ruminants, eventually agriculture, were creative and wildly successful. But they were workarounds. The underlying limitation never went away. You cannot eat grass today. Your neighbor cannot eat grass. Your child cannot eat grass. The most grass-adapted human who has ever lived could not eat grass in any nutritionally meaningful way. Despite 2 million years of living surrounded by it, despite the extraordinary adaptability of the species, despite every cultural and technological innovation in the human repertoire, the beta-1,4-glycosidic bond remains unbroken by human gut chemistry. Cellulose remains indigestible. The cow remains unimpressed. The next time you're outside and there's a stretch of lawn underfoot, take a second to actually look at it. That grass, ordinary, boring, everywhere grass, represents one of the most abundant caloric resources on the planet's surface, and one that is, for you specifically, completely unreachable. Meanwhile, a goat would absolutely go to town on it. The human relationship with grass is a story about constraint, creativity, and the remarkable ways a species can prosper despite a fundamental biological limitation by building entirely new strategies around it. The grassland that should have been a dead end for a fruit-adapted primate gut became instead the stage for the entire sweep of human prehistory: the hunting of grazers, the tending of herds, the cultivation of seeds, the construction of civilizations on wheat and rice and corn, all because one family of plants locked its calories behind a bond that human chemistry couldn't break. And rather than waiting around to evolve the key, a small, lean, hungry hominin standing in that ancient savanna started doing something else entirely. That something else, compounded across 2 million years of ingenuity and desperation and creativity, eventually became the world you're living in right now, which is worth appreciating the next time you eat bread, or pasta, or rice, or anything made from flour. You're not eating grass, you're eating the solution.